Question 7. This question is about determining eventually turning the MR, the molar mass of a volatile liquid. The idea is you inject a sample of a chloroalkane X, and it's noticed that it's toxic. That question on that comes up in a minute, and we're going to inject it with a hypodermic syringe into another gas syringe at 97 degrees and the atmospheric pressure of 100 kilopascals. Now, because we're going to be working with gases in a minute, I've done an immediate conversion into Kelvin, which is something you should be thinking about, and then immediate conversion into pascals from kilopascals. So we're asked to work out the mass of X injected, so a subtraction. It's very important we consider the significant figures here. Mark was lost if you missed out that 0. There are 5 sig figs in both cases here, so this answer should be in 3 significant figures when you consider it's the decimal. And this point here as well, we got 1 decimal place, therefore 1 decimal place in the answer is appropriate. Again, I've done the conversion here. We're going to be working in meters cubed in a minute. That's the conversion in ideal gas. So it's divide by a million gets us to meters cubed. So 7.2, we're asked to calculate the MR of X and determine which of the haloalkanes it is. So we can use PV equals nRT to work out the number of moles. Moles is PV divided by RT. Rearrange the ideal gas law. Input the data from the question as shown on the previous slide. Gets us the number of moles here. I've gone for 3 sig fig. It's 3 sig fig for the kilopascals, 3 sig fig here, here and here. Molar mass divided by moles. We're going to join those two equations together, and we're then going to carry out the calculation, the 0.270 from the previous calculations, and that gets us to 79.1. That is the CH2Cl2 from the choice at the top. So suggests that a reason other than apparatus inaccuracy why the MR value determined from the experimental results differs from the actual MR. You could say about the volume of gas in the syringe is greater than the true volume, perhaps air leaked into the syringe, and when you work at MR then it's smaller than expected, because this value here, this volume, will be greater, therefore the number of moles would therefore also be a greater value, therefore the MR would consequently be a smaller value. Suggests the reason an appropriate safety precaution that the student should take when using the toxic chloroalkane X. Appropriate thing to do is to use it in a fume cupboard, because if it's a toxic gas, it could escape and cause harm, so carrying it out in a fume cupboard would be a good idea to avoid the toxic vapour. Question 8 about enthalpy changes. First of all, an equation with state symbols of the combustion of ethanol. So ethanol plus oxygen goes to carbon dioxide and water, balance it up, and then add the state symbols for the second mark. This is the enthalpy of formation of carbon monoxide. That hasn't been written. But why is this enthalpy change difficult to determine directly? Well, because it's very difficult when you burn carbon in oxygen. It's very difficult to form carbon monoxide, so carbon dioxide is also likely to form. Next we have to work out the enthalpy of change for the reaction in 8.2. This is 8.2. Using this data. The data we have is the combustion of carbon to make carbon dioxide and the combustion of carbon monoxide as well. So I've drawn this cycle. That's the reaction we want to calculate. This is the enthalpy change for the burning of carbon, the enthalpy change for the burning of carbon monoxide. So this is the direct route, this is the indirect route. If that's the indirect route, then this arrow needs to be changed, so this value changes as well, so it becomes plus 283. So the value is minus 393 plus 283 goes to minus 110. You can also use this equation as well. The enthalpy of combustion of reactants minus the enthalpy of combustion of the products will get you the same answer with the same calculation, just done a different way. Then we're going to use the data to calculate a value for the XEF bond in XEF4, an unusual compound, as it's a xenon compound. So what we're doing here, this is what we want to work out. This is where I start with what we're going to try and work out the enthalpy change. And then I'm going to try and construct a cycle. So I look at this and think, well, I'm going to have xenon and fluorine. That's one root there. That makes this compound in this equation. That's that link. And then we have xenon to xenon, which will be a zero enthalpy change. Enthalpy of formation of element is 0. And then we have this enthalpy change here, 2 fluorines making 2Fs. So 2 moles of fluorine making 4F. So double the 158 to make 316. Then that arrow is going the wrong. This is the direct route, this is the indirect route. We're going to flip this arrow around so it becomes positive 252 plus 2 times 158 gives us 568. Look at the structure of xenon tetrafluoride, and it will have 4 bonds. So we divide 568, which is the total enthalpy change for breaking the compound into its atoms. Divide that by 4 for the strength of each bond, gets us 142. 8.5 suggests a reason why the value calculated in 8.4 differs from the mean XEF bond quoted in the data source. Well, this is a very common question. It's all about mean bond enthalpies on average for XEF taken from a range of compounds, therefore are going to be slightly inaccurate.